Hello, my name is Junab Lee at Hankuk University of Foreign Studies. Let me introduce you my research. Presentation contains introduction, method, results, and discussion as in order. Let's start with the introduction. Quantitative analysis in MRI is challenging due to the bias field. Quantitative analysis needs to correct the bias field for desirable results. What is bias field then? The term bias field refers to intensity inhomogeneity. Such signal is a very smooth and low-frequency signal that can corrupt MRI images. The bias field causes intensity variation among the tissues which hold the same physical property. Such distortion might bring undesirable results. N4-ITK, the traditional method, developed it with non-parametric to correct the bias field. However, current method suffers from high complexity and time-consuming process. We propose Hampel Denoising Diffusion Model HDDNet. Such deep learning method can bring faster inference time, lower complexity, and same or even higher accuracy of its correction. We start our research by analyzing the bias field map, also refers to bias map. We ran through fit distribute R package to search which distribution best fit its intensity. From the package, we found that Cauchy-Lorentz distribution shows highest fitness through its density and CTF. Through MLE and Nelda-Mead algorithm, which optimize the location and scale parameter, we were able to find parameters as shown in right bottom of the slide. We modeled the mixture of both Gaussian and Cauchy-Lorentz distribution, setting its weight parameter to optimize the fitness to original MRI, aka corrupted image by the bias field. Through maximum likelihood estimation, we were able to allocate alpha, x0, lambda as shown at the bottom slide. To assess the fitness of Hampel function to the image intensity, the mean fitting error between the histogram and the probability function was calculated. The mean fitting error is 0.012 less than Hampel function, showing that it is a much better fit to MRI with the bias field, as shown in figure D. This study was approved by the Institutional Review Board. Our dataset is followed accordingly. Diffusion Denoising Probabilistic Model, aka DDPM, composed with two processes, forward and reverse process. Forward process model the probabilities of images with additional bias added to the image. After such T-step of forward process, DDPM denoises the random noise to target image with neural network. Our denoising neural network is basic UNet with first layer of 64 out channel. Model denoise the corrupted MRI to uncorrupted. Loss is computed between model output and N4-ITK MR image as label. Evaluation was took in both quantitative and qualitative. For the quantitative evaluation, MSE, PSNR, SSIM were used. Inference time was measured in same environment with training setup with 26 subjects. The qualitative assessment was done by comparing N4-ITK and HDDNet prediction of synthetic bias field. The synthetic bias field was generated from the trained image bias field merged to the test set. As shown in table, Hampel random noise outperformed Gaussian random noise in all matrix. Hampel mixture distribution can provide clear evidence of convergence. Right figure shows N4 and HDDNet follow similar pattern of the bias field in synthetic image, especially in the line plot. But as in table on the left, our model outperformed on its MSE and PSNR. While N4 takes average of 39 seconds to correct the bias field from its corrupted MRI, HDDNet takes about average of 4 seconds, which is 9.75 times faster. We propose a new bias field correction method with Hampel distribution. Our proposed method is more robust with automatic parameter settings on correcting the bias field than N4-ITK. We also point out that such deep learning approach is faster in time while still maintaining the accuracy. However, there are further evaluation are required through noisy MRI. Thank you.